Thank you for having me at this moment. Image retargeting is actually one of the things that I pursued during my undergrad and my master. In my PhD, I changed because it's very centered, and I'm now getting back to this team, but with a vision totally related to machine learning. So, besides image retargeting quality assessment via Deep Embeddings is how to assess image quality in a retargeting scenario. I'm going to explain to you in a few slides, and how just using Deep Embeddings is unethical. Okay, so what is this problem actually? My first contact with this problem was with this paper, SimCloud for content-aware image resizing. It's a very traditional and old paper. It's about 2007. It's an application to pretty much enlarge image while we preserve the relevant content. But this paper kind of led a lot of other applications. I'm going to show you in a few slides. But pretty much it search for seams, these red pixels path that you can see. They're optimal. You need to find them optimally. And then by researching or removing them, you can change the image aspect through any kind of application. Because back then in 2007, I don't know if you remember, like the cell phones, we don't have much of like pretty much every phone and every screen now, we have like a regular resolution. But back then we have like different aspect ranges for screens. These problems pretty much this. You have an image, like original one, you take this, but then you have to present that same content in a probably smaller space. So how do you do that? We have here the two main, in B and C. We have pretty much two of the main ways of doing this. You can just scar content by cropping. You can scale like deforming uniformly pretty much every part of the image, or you can have like a more sophisticated solution. This is one of those algorithms that comes from these stereoscript maps, and I like very much this example because it has a data set full of them. But like if you see the grid, like it's very like tiny, but you can see a few aspects here after the transition between the background. It's like a very good result. We can also use that to enlarge images and increase them. We also have content amplification. We can use that by combining those both, by increasing and reducing the image because you preserve the relevant content. And you can delete a few objects from the image. Imagine if you have this amazing tree, like, and then you broke up with your boyfriend or your girl, and then you can remove it, and you can still keep the good memories from that time. It's a very, when I first got in touch with the subject, I got very excited because I see the potential for a lot of applications. And it's just one single method, you just combine it in different ways. But then later in 2010, I guess, this study, a comparative study of image retargeting was released. And we have about 11 types of algorithms that try to solve this image retargeting problem. And this study actually assessed those algorithms as an attempt to show which one is better than the other. So you can use in real applications. So how this assessment works? Okay. What is the challenge by assessing images in this retargeting scenario? We don't have actually the same dimension to do that. So SCCM, I don't know if it's like this, or the VIF index, or even the mean absolute error is not possible to apply because we don't have the same dimensions. So we kind of need to have a metric that can encompass both subjective way of looking to that image and analyze some kind of content preservation. Earlier this morning, we're talking about a paper that used salient maps. Like in the past, people use a lot of this to see if the salience is preserved during that transformation. But we cannot perform direct crosslinks, and we do a semantic one. So it's very challenging for that reason. So we also don't have like a clear definition of how to. We don't have like this formula how to assess if a result is good or bad analytically. But we have these three main pillars of assessment. We must preserve the image content, the structure, and we must result in an artifact-free image. And you cannot deform, or sometimes when we have other algorithms that do this targeting thing, we might get like glitches in the images. So must to result in an artifact-free approach. This was my first work in this area. Okay, I tried a directional way. And this is like one of the quotes that is in my paper. I like this is very strong because you need to add the human look, not just analytically, to get feasible results. Because humans can tolerate a few type of formations, like in texture, but like geometric features, we don't like to see that much. We see that's a bad result on a course. Backgrounds can be distorted or reduced. We are fine with that, but like people and faces, we don't like that much. And faces are like one of the most type of images that have like bad results, because faces usually have like the cheeks, and it's like a very uniform region, and most of the algorithms work on those uniform regions. So have that. And how we do that to assess? We have pretty much, that's the thing, like this field has not evolved to the maximum. This work here, I guess, is about 2011, 2012. We have pretty much those two parts here. They have two main data sets. But like they didn't solve the whole problem, because it's kind of time expensive. Performing those studies. The first one, the one on the left, I don't remember exactly the number of people, but around 100. And they performed two kinds of studies to see if an image from an algorithm is good or bad. Okay, because this whole presentation is about how do you create one of those algorithms that can analyze one image and see that its quality is good or bad. But in the first study, the retargeting data set, it's from a computer science lab in MIT. Okay, it has two types of experiments. One that is, we call it unblind, because the observer gets to know the actual image, and it's presented only two of images from two different retargeting operators. And then it has to choose which one's the better. So we have like a voting for each image. Okay. But then it has like another type of test, which is the blind one, which you don't know what's the actual image, and then it has to choose one from another. This was done because they want to know if, just by looking the retargeting results, it has some kind of bias towards knowing what it's supposed to be and how it is. But they found that the results are very. Then we have this data set. And the thing about this data set, I'm going to show you later, because it's very difficult to provide great scores, quality scores, because we have just voting, and not all image pairs were actually evaluated through all the participants in this study. But it was with human objects. And this very one, it's the only IEEE transaction, like it's a very robust one. We have like different similar tests, but different. The CUHK, and we have actually a scale. It's not just good or bad. People would get the one retargeted image and the original, and we want to classify in one of those categories. It's bad, both very good and excellent. And you also have the unblind and the unblind in the blinded test to that, to know if it's a good result or not. In the first data set, we just have one metric, the candle tall correlation. It's about voting. It's a voting thing. It measures agreement between objective and subjective scores. But in DCUHK data set, we have actually one of what I like most about this data set is because you have actually a full experiment written to follow a path to get your grades. You're not free to do. There you're like more free than when you see most papers. It's hard to understand how most people get the numbers because they just form a correlation in a different way. Here you have like a benchmark, very well. So it's easier because we have a lot of metrics that we must extract to compare, like the mean square error, the outlier rate, the Pearson experimental correlation. Those RMSE and outlier rate, which does that when it's closer to 0, it's good for your metric. While the correlations you want to So what is like my current research about using Deep Embeddings? Firstly, when I was like my master's studying this image area in general, I came across with this selling sketch mark, which is where two people look. It's a very nice paper. It's a very long paper actually. If they have like this benchmark, you get access to this test is fixation prediction. You must still predict where people would look in an image to know what's the relevant part of it. But then they just give you the images. They don't give the labels. You don't have access to those maps. And you must submit it to a application online. And then like there is a robot there, a system that give you the scores. There are 6 scores that they do that, and they rank you. I tried like in 2016. I got the thing that they have also like dummy models, like biased models. Which I think that's very interesting to when you have a data set and you use biased models to know if like your model can top something. Like for instance, usually when you take pictures, we like to center the objects. We have like this bias. So one biased model, biased model is like just putting a Gaussian in the center of each image because it's a way to get most of to catch this center bias. And if you score poorer than this model, you kind of have to redo your research because you're doing poorly than a fake model. It's very nice because it has like a few baselines, like the human, like the expert, the naive one, the center bias, permutation model, and that chance like that. Just throw random scores and see how it goes. When I read this paper, I find wow, what an interesting way of accessing results in image. And I try to get the same vibe of this paper to put into the analysis of mine, because when I'm doing research, not all the time I kind of got the results, but I found that my model has some interesting features that I can present to the audience in general. So this paper kind of ended up in my mind. Well, not just using a table to represent it, but to present it, just discussing about the model features. So, like I was saying, like there is these center bias, random ones, so it scores, and you have like this, which is a rank. They don't get it anymore. We have like a baseline for humans, because there are people that were actually using those helmets with cameras that catch what you're looking at. So I got inspired by this paper and did a different analysis from the previous data set in image retargeting. So this is, the name is actually because I'm working in this model with one of my students back in Brazil. He chose the name. It has this. Since he's doing like the work and thinking about that, we are pretty much using two types of embeddings from two different relational encoders, and we imply simply model architectures like flat net convolutional networks with residual convolutions, residual connections, and some with attention, simple headed attention. And when we get those embeddings and use those architectures, we end up talking the results. And here we have like the baseline models that we created to analyze that. Some of them are like pretty much half of this table don't even work as a human. They are not they do not score as good as a person. So there's room for improvement. We kind of overtopped like the experts, like one person that was participating on this study and has the best agreement between all the agreements that we have. So it's nice. It's actually under review. So I did not have like, it didn't submit it to archive or anything like this. It's the results. And it's the product of my student's master. That's pretty much this. But it's fun because we did achieve a lot of things with using deep embeddings. Like the field has somewhat is frozen. People are not studying this anymore, but there is a lot of room for improvement because the last result was about the correlation around 80%. So that's it. Thank you.